All right. So now we saw how we can build a model. We can adjust things and stuff. It's good to talk about saying, okay, what do we want to do to make sure we don't overfit, optimize, and all these different things, right? So let's first talk about overfitting, because that's a big danger, right? So one thing about neural networks that we talked about before is that our neural networks are really great at finding complex solutions to complex problems. However, note that also can be complex solutions to not complex problems. We might make it too complex, and this is where we get into the danger of overfitting, right? So one thing to check if we're overfitting is using this train validation test sets, right? And this will allow us to basically evaluate our model. I kind of gave this scenario before. This is why I've repeated this a few times, I think, with my cohort, but if you guys haven't heard it before, I kind of think of it as like the model is like a student, and you can think of your training, your validation, and your testing set as kind of like different ways of like, or different parts of the student studying for a test. So your training set is kind of like the data that you're looking as a student and like going over. You have maybe the answers in the back of the book, and you can practice it over and like, kind of keep changing up and like practice, 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 practice. Your validation set then would kind of be a take-home practice test. So you would know the answers, but you wouldn't try to take the practice test first. You would try to study as best you can and then use that to evaluate how well you're learning. It's like, did I actually get what I'm supposed to? So you can kind of see the scenario here is that when you're studying for a test, you want as much examples as you possibly can. You want as many things as you possibly can, learn as much as you can. And then your validation set, you really don't want to touch that until after you're done really training through, right? You don't want to learn off your validation. But let's say you start studying, your practice examples and stuff like that, and then you do your validation test, right? And you're like, oh, like my practice test said I didn't do very well. Well, then it's like, okay, you might go back and try to practice some more. And then maybe you kind of forgot about your validation set, right? Like your validation practice tests, and you go back to it and see you did better. You want to be careful, right? Is that you have to realize like maybe I'm remembering the practice test answers and I don't want that. So this is where you can kind of say, okay, like I think I'm ready for the test, but I'm not quite, right? And this is where you have to be careful knowing that you'll eventually overfit in the validation set as you practice more and more and more and evaluate yourself. So at the very end, to really truly judge how well you performed, you would have this final test, right? Which is your testing set. And that final test, final exam is when the students has done their practicing, their training, right? They did their validation / practice tests. Now they're in their final. And that's the way for, the school or whoever, right? To judge how well the student actually has learned. That's kind of like how we use our testing set here, is we're judging how well the model will actually perform. Your testing really should be done once. You shouldn't use your test over and over again as you iterate over the model. The reason why is because, again, you can subtly basically start overfitting to that model. So you have to be careful with that. Okay, does that make sense? Cool. And then usually we say our testing is our holdout, meaning that you take it and then you put it away and don't touch it until you are done with testing. That way you're not, mixing in with the data. Many models, many research has realized like they have data leakage where their testing data actually gets into their training validation, maybe when they're starting to clean, or maybe at some point they mix up the model or something like that, or there are examples that are actually in the testing set, but they're copied into the validation or the training set. So holdout's really important. Quick thing to note too is that sometimes you'll hear validation sets be called dev sets or dev tests. They're interchangeable, they're the same thing. Just depends who you talk to. And then your validation test set, they should come from the same distribution. And the same kind of idea, like why we should make sure our validation and test set come from the same distribution. You can just
randomness.
So randomness, can you go a little more detail than that?
No.
Okay. That's all good. I used to have, I had a professor who told us back when he was like in a physics class, he would always say there was one person who would be the 0 or 1 guy, and he would just say 0 or 1. And he's like, he didn't know the answer. He just always said that. So randomness is a pretty good answer. So yeah, I think part of the thing might be you use randomness to kind of like see, you want to make sure that your validation and test set are similar to each other in the sense that you're not having examples in your test set that are not in your validation, right? Because otherwise your validation set is like, oh, it looks good, everything's 100% awesome. And then you do bring your test, you're like, oh, like I didn't think of that example. I think I'll give you a really quick example of this, like for self-driving cars. Imagine you have some machine learning model that figures out how to drive a self-driving car, avoids people, avoids cars and stuff like this. But they never, in the validation set or even the training, but especially in the validation set, they never had an example of someone jumping in front of a car. Well, you might say, wow, my self-driving car is perfect, right? And then in the testing set says, what happens if someone jumps in front of the car? It's like, oh, it didn't know what to do. Turns out it just runs them right over. Like, that's not good. So those are the kind of things that you'd want to have. Okay. So this actually turns out to be a big part where also as your data, like let's say you deploy your model out there, you want to make sure that you iterate over and over again as like the testing set and the data that you're receiving changes. So for example, when you talk about A/B testing, right, it's kind of very similar, where the first few people that kind of join a service are going to be very different probably from the people who are going to be joining in like a year or 2 years. Think of the first people who joined YouTube versus the people who are joining YouTube now. It's like, it's going to iterate and change over time. So you have to constantly make sure you're updating your validation test sets. Okay, cool. So always something to consider. All right, but wow, I wasn't talking a lot about this training validation set. So our model complexity graph. So this is true for like machine learning, so I won't dwell too much on it. But basically the idea here, underfitting, you have low complexity, right? You have high bias, low variance. Your training error is large. Your testing error is large. Basically, your model is pretty crap. It doesn't do a great job, right? So you're underfitting, okay? Opposite of this overfitting is where your model thinks it's like super confident. It's like, yeah, I know this answer, right? It's aced all of its training stuff like that. It's done really well in the maybe validation, but like its training is like, oh, 100%, right? But it's not quite doing well on that testing part. It's got a large testing error. This is where we have low bias, high variance, right? So basically the idea here is if you're underfitting, you want to raise the complexity. If you're overfitting, you want to lower the complexity. So in general, you'll see something like this where you compare your training and testing, or really should say training and validation. It will look something like this, where essentially you can think of like number of epochs, right? Think over time and stuff like it's learning more and more. And this training error is like, boom, it's going down. It's getting like right there, it's getting like almost no error, right? Like almost 100% correct. But your validation error, you'll see, might start popping up like this. And as it's popping up like that's like, hey, this is no good. Like this is mean it's getting too confident here. And it's actually making mistakes because it's just basically memorizing the answers to the training. So you actually want to stop it around here. So one solution to this is called early stopping. Now, I will note that in the curriculum, if I'm being honest, I don't quite agree with how they do early stopping. I think that's not the right way to do it. So in the curriculum, it mentions about doing early stopping and just says, don't like say, oh, you do 250 epochs and say, oh, okay, let's stop it. You see this validation, it's like, oh, let's stop it around like 80 epochs. You could technically do that, but then you have to run your model like twice, right? And so it's not necessarily like the most efficient way to do this. Imagine you have a model, like it's fine if you're running it for 200 epochs, takes like maybe 10 minutes at most, pretty quick. But if you're running a model and it's gonna run like, 4 hours, it wouldn't be really fun to realize like, oh, I gotta run this again for only 3 hours this time. It'd be kind of inefficient. So what's nice is that Keras does have some implementation in there that you can actually use to kind of check, do early stopping. Sorry, does someone have a question? Okay, cool.
No.
Okay, thank you. All right, so one thing we're going to use is something called model like callbacks. So callbacks are really nice because basically as the model's training, it's going to do what's called callback. It's calling back a function and doing something with that information. So in this case, a model checkpoint is a really nice one. Basically say, hey, save the best model. So this best model right here, like this, remember we can save our model. We can actually say, all right, from this callbacks, model.checkpoint, and there's some other parameters here as you can do as well, but it'll save the best model, right? Note this is say best only. I'll talk about this in a second. But basically, as it trains through, sometimes your model will do really well, and then it'll say, oh, like this validation starts going up again. You don't want to have the model under here. You would like to have the best model right here. So you can actually say, let's just save this best model. So what's nice is that if you run this for like, 5,000 epochs and it figures it out after 50 epochs, it'll still run all the way through, but it'll save the best model and won't have to like give you a bunch of like, crap model at the very end. So it's a really useful thing. And then of course you can just load your model at the very end. So you can like run this like little set of code essentially, and then like step away and then come back and say, cool. Now, obviously, this might not be the best thing, right? Like, imagine you're working and it's like, oh, like, what are you doing? It's like, oh, I'm running my model, it's like for the past 4 hours. You're like, well, that's not super efficient, right? Maybe you actually want to do something with that model before going through. So some other things we can do is something called early stopping callback. So the idea here with model checkpoint, you still run through the whole thing, but you basically save that best model. And for early stopping here, you can actually say, all right, just stop training once you reach a certain point. So this right here basically is saying when you reach a certain error, so your error is not really dropping anymore. So you can imagine like this validation is either kind of flatlining or even going up. Then basically says, okay, if it's not training, if it's not learning at a certain point or it's getting worse after so many epochs, just stop right there and we'll keep that model. So that's what this right here is. It says monitor some kind of metric. In this case, validation loss. Our minimum delta is basically saying how much of a change in the loss, in this case, the validation loss, how much change counts as improving, right? So if you set this to 0.01, it has to change at least 0.01 to count. An extreme value of this would just be 0, meaning that like the model loss like never changes, which is the default on here. And then patience here, it's just saying how many epochs do you wait. So maybe like, for example, if you set patience to be 1, it waits 1 epoch. It's like, oh, it didn't do very well. That next one. And then the second epoch, like, oh, it didn't improve again. We're going to stop it here. You might let it run for a few epochs afterwards to see, give it a chance essentially to try to improve itself. So in this case, it'll wait 5 epochs. So if in 5 epochs in a row, it doesn't change, it's like, okay, buddy, like you're done here. You're going to go home now. Okay, cool. Does this make sense to everyone? Okay. One thing I know about the model checkpoint too, you can also have it save multiple models. So as it's going through it, which can be really, really useful. So what's nice too, I believe in the documentation here, you can actually format this like this, like with like kind of F strings and stuff like this. You can actually format this like this right here. And you can actually save what specific epoch and what validation loss it has. So this can be really useful. For example, if you set, you set and forget it, you're like, all right, 4 hours to go. It would be really awful to find out, like, you're like, oh, like it was best right here, but you stopped it over here. And you're like, oh man, I gotta go all the way back. You can actually keep those models individually and stuff like this and explore maybe a little bit more. So kind of useful to have. Okay. And that's also note that if you're doing that, if you're saving multiple models, you don't want to save best only. You want to probably set best only to false. So that way it's saving multiple models. Okay.
All right, Victor, why would you want to see all the models? Like, why wouldn't you just want the best model?
Yeah. So one is like, you probably just do want the best. You might want to save models at certain epochs to see how well it's performing. Maybe there's multiple aspects and stuff like that. You want to explore a little bit of like how well it's doing, or just a little more, what's it called? A little more exploration, like how that model does. And maybe this, for example, is not your final model. Like if this is not your final model, you wouldn't want to keep just the best one. You want to see, okay, how can I improve it later on? So you might do something like that. Good question though. Yeah, at least that option is there too. In general, you probably will have this. Just say the best model because you're like, I only want the best, the best student. I don't want, second place. I only want first place here. But sometimes second place needs love too. Okay. So anyway, this is a good early stopping thing. I don't think the curriculum really talks about it in this way, but I thought these are important because they're really used. Okay. So now we can talk about when a good model goes bad. So we talked about overfitting. Basically, overfitting means large weights, the model's too confident, and it means you have to punish the model, right? And just like every good parent, you don't want to punish your student, your kid, but sometimes you just got to tell them you're doing it wrong. You got to do the right thing. So that's really where regularization comes in, right? Is that our regularization is going to punish large weights. It's like if it's thinking it's too confident, you're like, listen, buddy, you're only 3 years old. Sure, you might think you know everything, but you probably don't. Let's not be so confident on this. And that's really what this model is doing with the regularization. So there's a couple ones we've seen before, L1 and L2. Give me a thumbs up if you guys remember L1, L2 regularization. Cool, I see lots of thumbs up, so I won't drill too much. But L1 basically, right, is your absolute value. And note that we're basically modifying this cost function, J. So the idea here is like we have our loss function, right, for each individual point. And we have some factor lambda that's going to basically, what's it called? Be this is kind of like our hyperparameter. We say how much are we going to punish extreme weights. Remember our cost function, we want to decrease what's it called? We want to keep it as small as possible, right? So by putting this lambda factor in here, we're going to automatically say, hey, if you got a large weight, we're going to go ahead and bump that up. Like it's going to be even worse. So the idea here is that it'll reduce the weights. L1, if you guys remember, basically it's really great for feature selection. It'll tend to make small weights go to 0. Not small, just go to 0. Or sorry, not small, but it'll go to 0, meaning they'll kind of disappear. In this case, you can just remove them. This is really good for getting like sparse, a sparse model. So you might start with like a really big model, like with many nodes with many weights. And then you run this L1, for example, and it'll start getting rid of some of those connections, some of those nodes. Like, hey, this thing is not doing very well. We're going to set this to 0. And then you can just basically get a smaller model. So it's a nice thing to have. But in general, we'll probably use L2 regularization, which again, if you guys remember, uses like the squared value. So it's the same idea here, but instead of using absolute value, you use squared. And this will basically keep almost all of the, all the points in the model, right? So all the weights. It'll tend to, still make them smaller, but they won't go to 0. They'll just get smaller and smaller and smaller. Now I note that I put here tends to give better results for training. The reason for this is kind of interesting. Basically, it means that our weights tend to be more consistent, like not consistent, but like more even with each other than like an L1 regularization. So the way I kind of say this is like, imagine we have two vectors, 1, 0, and 0.5. Let me go ahead and write this down here. So we have 1, 0, and 0.5, 0.5. Okay. If we just take the absolute value, if we take the absolute value of here and then add them together, right, this is just going to be 1, right? So absolute value of 1, 1, absolute 0, 0, right? Add them together, 1, right? And we can say that's going to be for absolute value. If we square it, we'll get the same answer too. 1 squared is 1, 0 squared is 0. Add them together, we just get 1. We'll put square. Okay. So these are pretty high, right? Remember, we want something small. However, 0.5, 0.5, if we do absolute value here, we get 0.5 plus 0.5, 1, which means it's just the same thing. Basically, for absolute value, L1 regularization, these look the same. They're like, yeah, either of these are fine. Like, so it'll tend to go towards the 0 part, right? Because we start getting rid of it. But with our L2 regularization, you actually see 0.5 squared plus 0.5 squared. Well, that's going to give 0.5 here, which is going to be 0.25 plus 0.25. This will be 0.5. So L2 regularization will tend to prefer these kind of vectors where they're about equal. So this tends to actually be really good because it turns out it's kind of like, why would you give it all these like nodes and like layers without like you wanted to find more complex parts. So this tends to do a little bit better in training because you're basically using all of the nodes to try to solve something versus trying to get rid of nodes. Okay. Does that make sense to everyone? Cool. All right. So next fun one is dropout, which seems super counterintuitive, but what we're basically going to do is we're going to purposely say, don't, this neuron, don't even use it. Don't even bother training on it right now. And so the way I kind of give this analogy is like, imagine like if, if you're working like your arms or like it's leg day or arm day, right? You don't want to train like the same, like if you were like lifting weights, you don't want to use the right arm constantly because eventually you'll get into this like weird part where basically your right arm's super strong and your left arm's like super weak, right? So neural networks kind of the same way. What tends to happen is like if the neuron is already really large, what will tend to happen is that it'll stay large and then it'll continue to use that one and it'll ignore everything else. So we want it basically this neuron, like we want to tell the neuron like, hey, we want you to use the whole structure. We get that you like using, this neuron. It's your favorite neuron. We get that. But maybe this time around, maybe don't use that neuron today. Like try this part. And that's really what Dropout's doing. So what's happening here is that we have our big neural network right here. And every once in a while, or not every once in a while, every training, every epoch, right? We basically just randomly choose a certain percentage and say, hey, go ahead and just like drop out, like just randomly choosing, drop out this one, drop out this one, and drop out this one. And so basically you connect these and say, hey, you can't use these anymore. And it has to use a smaller network internally. And then you say, okay, you train this, you do the back propagation, right? So these weights won't be adjusted. They basically stay the same from these neurons. And then say, okay, it's a new epoch. So we go ahead and say, all right, let's choose some randomly again. And we choose these ones, for example. And so the idea here is that we're actually going to purposely not use neurons every single epoch. And this might sound like, it's like, why wouldn't we use every neuron, right? It seems like a nice thing. The way you can kind of think of this too is that you're basically training multiple neural networks. You're basically training different neural networks every single time, and you're basically improving on each part. So there's actually, I'll mention to you guys later, but like I already talked about this book, Hands-on Machine Learning with Scikit-learn. I'll send you guys the link in a second. But he actually does this great scenario. It's kind of like equivalent to like saying, if you had a company and just randomly told people, hey, you're not going to work today, just take the day off, and then have people come in. You can imagine how like crazy that sounds like already. It's like, hey, imagine like, Joe from finance, is like, or Joe for like, I don't know, bookkeeping or something like that, is not coming in today. And like, hey, but Joe needs to get this done, right? What's going to happen is that other employees basically are going to have to like pick up that slack constantly. So everyone's going to have to be a little more generalized. Everyone's going to have to know a little bit of how to do things. If you had one person, basically a key man, and they kind of go away, you're like, oh no, the whole company is screwed. Like we can't do anything. That's the idea of a dropout too. In practice, he kind of mentions like he's like, I don't really know if this would work in the real world if you actually told people to like not come into work like that, if it would actually help the company. But the idea for neural networks, it does actually work out really well. Note that in general for sequential neural networks, 20% dropout is pretty typical. Next week, when we talk about convolution neural networks, you tend to have a higher dropout just because there's more complexity in there. So you might have something like 40 to 50% dropout. So yeah, okay. Any questions on this dropout then? No? And just to kind of show you guys really quickly what this looks like, it's just a separate layer. So you can see here, I actually input this new layer here, and you actually add it as a dropout layer. So you have like your dense layer, your dropout layer, and then dense layer, dropout layer. Typically, you would do all your dropouts. I think it's like about like if you're having a really deep neural network, you probably only do dropout about the third to maybe fourth layer. And that way you can keep some of those more complex values, keep learning versus the very early stuff. So in general, if you have a really deep neural network, you might only have like 3 dropout layers, basically one after each one. Okay, cool. Sound good? All right. So, all right, optimization should take a little quick, but it'll be fine. All right, we have a few minutes left.